Alright, so in this video we're going to do rotational inertia a couple of times just to see examples. So the first thing, we're going to have a massless rod, so we're going to ignore the moment of inertia of this, with two masses connected to it, each with mass m, and we're going to call this length from here to here is L over 2, okay? And we're going to rotate it about this central axis here. So we have two masses rotating. The other option is we're going to have one mass located at the central axis of rotation and the other a distance L, so they're the same distance apart, but this one's now further away from the axis of rotation. And so the question here is, if this is option A and this is option B, which system here is going to be easier to rotate and which one's going to have a greater moment of inertia? So I want you to guess. Between these two, which one do you think has a greater moment of inertia? Okay, well, let's go ahead and see. I'm going to go ahead and do the first one, and then I'll have you do the second one. So moment of inertia for a particle, remember, is mr squared. And so for each of these, they're a distance away from the central axis of L over 2. So we're going to say, okay, so m times L over 2 squared for the first one, plus for the second one, m times L over 2 squared. And so we get ml squared over 4 for each of them. And we add those together, and we get 1/2 ml squared as the moment of inertia for this system. Okay, now you go ahead and find it for this second one. Well, when you do it, using the mr squared again, for this one it should be 0 because it is 0r. For the second one, it has mass m and length distance away L, so just ml squared. We add those together, we get ml squared. So you can see that this system here is twice as hard to rotate as this one, and the reason why is because it's the r squared. So we have a greater impact from having radius further away than we do from having radius closer up. Okay, and so when we shift this way out here, we're really amplifying the difficulty of rotating it. Okay, so you could think of it like a yo-yo. So if you're spinning a yo-yo in a circle, the longer the string, the more difficult it will be to rotate that string. Okay. Okay, so for this next one, we're going to look at now a meter stick. Okay, so let's say that we have a meter stick. All right, so meter stick means it has a length equal to 1 meter, and we're going to say that it has a mass of about 60 grams or 0.06 kilograms. And the question is, well, what is the rotational inertia of this? Now, actually, let's see this. Let's say it's rotating around its central axis with an angular velocity of 5 radians per second. Okay, and we want to find its kinetic energy. Okay, so how much energy does it have to be rotating like that? So it's got some central axis here. So in order to do that, well, that's 1/2 times I omega squared. We know omega, but we don't know I. So option 1 is we can integrate, which I showed you how to do in the last video. Or, since we've already integrated this shape, it's a uniform rod about its center, we can actually look it up in our table. So if we look at our table here, okay, which shape? Well, I guess I kind of told you. It's this shape right here. So uniform rod about its center, and we could say that it's thin, right? So a meter stick doesn't really have a radius this way. It's very small that way, so we can kind of ignore that piece. And so we're going to use this. So 1/12 ml squared is the rotational inertia we need to use here. Okay, so if rotational inertia is 1/12 ml squared, we'll say, all right, 1/12 ml squared. In this case, m is equal to 0.06 kilograms times our 1 meter squared. We'll go ahead and simplify. So we now have a rotational inertia of 0.005 kilogram meters squared if we simplify that, which we can now use to calculate the angular kinetic energy. Okay, so we'll say 1/2 times 0.005 kilogram meters squared times our angular velocity of 5 radians per second, and that's all squared. Okay, we simplify that, and now we have to focus on this part. So we say, okay, for units, we get 0.0625 kilogram meters squared radians squared per second squared. And so the radians and the meters kind of cancel together because these meters represents like a radial distance, and this is meters kind of per radius, I guess. So we cancel these out, and so we get kilogram meters squared per second squared, which is a joule. So we get 0.0625 joules. Okay, and so that's with the uniform rod. And I'm going to show you one more shape, and then we'll wrap up this video. Okay, so for this one, I'm going to have you kind of do most of the work. So we have a uniform disc. Could be like a cylinder, and it's rotating about this axis. Okay, and it's going to complete one revolution in 2 seconds. Okay, it's going to have a radius of 0.3 meters, and it has a mass of 1 kilogram. Okay, so what we want to do is we want to find the rotational kinetic energy for this object too. Okay, so 1/2 I omega squared. So first step, we're going to find I, our moment of inertia. So when we look at our table, we can say, okay, well, if it's a disk, which of these shapes should we use? Okay, do you want A, B, C, D, E, F, G, H, or I? Which one do you want to use here? Well, we should use this one right here. It's a uniform disc, so we're going to use the 1/2 mr squared. So then go ahead and use that and find out what I is. Okay, 1/2 mr squared. Go ahead and calculate I for us. So we get our moment of inertia to be 0.045 kilogram meters squared, which we can plug in for there. We also need our angular velocity. So we know how many revolutions it completes in 2 seconds, but we need to know how many radians per second. So I want you to try to figure out what our angular velocity is in radians per second. Okay, go ahead. Well, to do that, 1 revolution is 2 pi radians. So divided by 2 seconds is going to give us pi radians per second. Okay. And now let's find our kinetic energy. So go ahead and find your kinetic energy. And so we end up here with 0.22 joules of rotational kinetic energy. Okay, so hopefully this gave you kind of a start with finding moment of inertias. This is basically it. There's one more piece that we have to add on that makes things a little bit more complicated, but this is the basics of finding rotational inertia.